So my name is Owen Craven, and I will be presenting on my work with the time series snow accumulation, and my work in creating the first ever annually resolved time series snow accumulation database for Antarctica. To begin, we need to talk our terms. So, what is snow accumulation? And simply, my definition of snow accumulation is the same as surface mass balance, or SMB, which is the amount of deposited snow subtracted by the amount of ablated snow. And that leaves you with your total snow accumulated, or the surface mass balance. So if you have 12 inches of snowfall in Antarctica, and then during the summer, 3 of those inches melt off, your total snow accumulation would be 9 inches. And the question is, why do we need to know Antarctic snow accumulation? Why is that even important? And snow accumulation gives us a better understanding of climate change. In order to understand our present climate, we need to know what's happening in Antarctica. And by looking in the past at the snow accumulation in Antarctica, we can begin to understand how our climate is changing and make inferences in the future of how our climate can possibly change. It's also important to understand our ice sheet mass balances, which is simply the amount of snow coming into an ice sheet subtracted by the amount of snow coming out of an ice sheet. These ice sheets also dominate sea level rise, as we expect that as temperatures continue to increase, that we'll receive more precipitation in Antarctica. And we'll also have more melting in Antarctica, which will contribute to sea level rise. And the snow accumulation is a major input to these ice sheet mass balance equations. And by better quantifying that, we can better quantify sea level rise and understand how our ice sheets are changing. So the question is, how do we get the snow accumulation data? As we were kind of joking about before, Antarctica is a hostile place sometimes. And the answer is through ice cores. As the snow accumulates, it builds up, and it turns into ice. And by drilling into this ice and accurately dating these ice cores, we can measure the amount of ice in between these years and calculate the snow accumulation. So what's the big problem? We've drilled lots of ice cores, and we have lots of databases with snow accumulation values. The problem is that these values are recorded in multi-year averages. So for example, here's an image I took of a snow accumulation database that you could find on the internet. And each of these rows represent an ice core. As you can see here in this ice core, it starts in 1899 and ends in 1996. And then the surface mass balance is 50. So that means on average, from 1899 to 1996, we get 50 water equivalents of water, 50 water equivalents of snow deposited at this location in Antarctica. But since it's only an average, we have no idea what happened in the early 20th century. We have no idea what happened in the later half of the 20th century. All we know is that on average, we get 50 water equivalents of snow, which is a good start, but it doesn't show us a step-by-step change in our climate. So what we need is a time series data at a smaller resolution. And that was my goal, was to make an annually resolved time series snow accumulation database, so that we can really see these step-by-step changes. So that was the goal, an annually resolved time series snow accumulation database. So methods. As any good geologist, you need to spend some time in the field to really understand your area. And in my case, I was lucky enough to work in the library. And if you haven't been to the library, I suggest going. It's a wonderful, beautiful place. But what I did, I searched the library for time series data, for snow accumulation data. And then I separated this data from the accurate to the inaccurate, because I wanted this database to be a very accurate and trustworthy database. And then I organized this data into the database. And so it wasn't a matter of simply looking up articles, but I had to read the articles and understand the methods to understand whether this data was trustworthy or not. So let's talk about a little bit about some of the accuracy parameters. I wanted this database to be accurate, and so I set up some standard parameters. And according to a recent article by Majan in 2007, he described several common methods of dating ice cores. And he gave them a C, B, or A grade, depending on their, in relation to their accuracy in providing an accurate date. So for example, snow stratigraphy here is given a C, meaning that it's unreliable and inaccurate. And snow stratigraphy is taking summer melt layers and counting back the summer melt layers to try to date the ice core. As you can see, that'd be very subjective. Some people see a summer melt layer, some people don't. The melt layers may be eroded away, so it doesn't give a very accurate description. Chemical markers such as an isotope, such as oxygen isotopes, hydrogen isotopes, they're giving a B grade simply because, once again, it's subjective. It's more accurate, but it's still subjective, and sometimes these layers are eroded away. And then finally, the methods that we used to create the database were these A grade, meaning that they are accurate and reliable. And we consist mostly of anthropogenic radionucleotides, which is simply nuclear bomb debris, volcanic horizons, and multi-state measurements. And we don't have time to talk about all of these, but let me talk about these A grade data. So what do these mean? For volcanic horizons, in a volcanic event, it can be eruptive enough that it ejects debris into the atmosphere. And this debris settles across the entire globe and settles in Antarctica, where it's deposited into the snow and is preserved in the ice record. So we can go back, and since we know the exact dates of these volcanic eruptions, since we know the exact dates of these volcanic horizons, we can accurately date that ice core. By finding that ash layer, we know when that was deposited. In a similar manner with the anthropogenic radionucleotides, what we know when these nuclear bombs blasted, which ejected debris into the atmosphere. And was once again settled over Antarctica. By finding these radioactive layers, we can accurately date the ice core. And then the simplest to understand is multi-year state measurements, where you simply get a snow stake, you put it in the ground, and you come back every once in a while and you check to see how much snow has buried it, or how much snow has melted away. And if your scientist knows how to work a ruler, it's a very accurate method. So after combing through hundreds of databases, hundreds of articles, this is what I came up with for snow accumulation data. Nice coverage of Antarctica. Once I ran the accuracy parameters and I separated out the time series data, this is what I was left with. A much smaller picture. We have some areas here in the coastal regions, but here in the heart of Antarctica, the interior, there's not a lot of data. Which at first was a little discouraging, but at the same time, it shows the current state of where we are in Antarctic research. And it shows where we have accurate data, and we understand where we need to go now in order to complete the picture. So after compiling all this data, I named it the ASAT database, simply standing for Antarctic Snow Accumulation Through Time. And this database has over 8,000 data points, which represents years with snow accumulation values for 410 locations across Antarctica. However, one of the problems is that these areas are confined over relatively small geographic locations. Once again, you need to remember that Antarctica is a big place. So this relatively small geographic location is the size of the United States. It shows just how little data we have in Antarctica, and how important every piece of data we use needs to be accurate, and we need to be collecting this. And that's why this database is so important. Whereas before this data was inaccessible, now it's accessible. The oldest core ranges from 167 AD to 1997, with more recent cores covering up to 2010. So when you compile all the cores together, we have an annually resolved snow accumulation time series from 167 AD to 2010 AD, which is a nice step-by-step look into this climate change instead of those multi-100-year averages. So here's an example of the database which I created. So you have the name of the ice core station. It gives the longitude and latitude. It gives the elevation if it was recorded in the article, or the units, and then the researcher. And then here in these two columns, it gives the year with the snow accumulation value. So we see in 1953, we had 353 snow, water equivalents of snow deposited. 1954, 161. 1955, 93 at this location. So now, instead of having from 1953 to 1959, we have 150. Now we see the step-by-step changes. So, next steps. Currently, we are working with the statistics department to create a snow accumulation map using a statistical model. Snow accumulation maps have been made before, but they didn't have any bounds on certainty or uncertainty. But using this statistical model and this data which I accumulated, we will be able to make a map with error bars, which will be a big step. We also want to identify negative and positive watersheds in Antarctica, these ice sheets, to understand where snow accumulation is increasing, where it's decreasing, and of course we also want to expand the database. We want to put this out there so that more researchers will be promoted to record this data, and so that our database can grow. So in conclusion, the ASAT database allows access to annually resolved time series snow accumulation data, which before was inaccessible. I consider data to be accurate if it was based on volcanic horizons, anthropogenic nucleotides, or multi-year state measurements. And this database now opens the door to really understanding the changing climate trends using snow accumulation values in Antarctica, whereas before, we couldn't do it. Are there any questions?
The ice core data goes back much farther.
Yes.
How far back does the ice core data go?
Well, our time series only goes back to 167, but other ice cores, it can go back thousands of years. Like, some might be able to help me out here, like 2,000.
The oldest one in Antarctica, in terms of the oldest ice core data, close to 1 million years, but it's not, accumulation data doesn't usually go back quite that far. It's usually temperature, isotopes, greenhouse gases.
How do they determine the age of the core?
Of those really old cores, or just these cores?
Both. You use these geologic events in our time, I assume.
Yeah.
How about for the ones in the past?
Yeah, so we can use those events. In the past, it gets harder and harder because the way that the snow makes it shrink and shrink and shrink and shrink and shrink, and so it's more tricky. By using chemical isotopes, there's seasonal variations in the spring and in the summer and the fall of these chemical isotopes, so we can just melt down the ice cores and measure these changes in the isotopes and count back that way.
That's how they do that. Okay. So have you looked at the relationship between the amount of snow or the ice accumulation and the sea level change, like since the last ice age?
I have not, no.
That to me would sound interesting.
Yeah, no, for sure. The first step was just to make this database, and now
there's probably not enough time to compare what you've seen in the last 100 or so years with the sea level rise that's taken place during the time of your study.
There's been a couple studies that have been looking at that, and there is a positive correlation to glacier melt and ice sheet melt to sea level rise, but I personally haven't looked too deep into that yet. Good questions, thank you.
Yeah, very interesting.